Hello and welcome to a new module on derivatives. Today, we will explore the concept of successive derivatives and the Taylor polynomial. The requirements for this session are quite minimal. Basic knowledge of elementary functions and some proficiency in basic mathematical operations will be sufficient. Let's begin by understanding what a successive derivative is. Imagine we have a function that is differentiable. When we take its derivative, we obtain a new function. If this new function is also differentiable, we can proceed to calculate the next derivative, which is commonly referred to as the second derivative or the derivative of order 2. In modern notation, it is often denoted like this, while in classical notation, you might see it represented as follows. What occurs if the second derivative is also differentiable and we can find its derivative? In this case, we obtain what is known as the third derivative, often denoted as f prime 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 of x in modern notation, or the third derivative with respect to x 3 times of the function f of x in classical notation. I haven't explained it before, but I'll clarify it. This notation is read as the second derivative of f of x with respect to x taken twice. How do you write the fourth, fifth, and sixth derivatives? Here's a demonstration of how to express successive derivatives in the case of a derivable function. The fourth derivative can be denoted using Roman numerals. Be cautious with this notation. The fourth derivative is represented as the fourth derivative with respect to x to the fourth, multiplied by f of x and so forth. The nth derivative would be simply denoted as f, with a superscript n in parentheses of x as seen in modern notation, and in classical notation, it would be the nth derivative with respect to xn times of f of x. Let's start with a straightforward example, a fourth degree polynomial. We'll proceed to calculate the fourth and fifth derivatives of this polynomial. So let's explore the impact of multiple derivatives on polynomials. Starting with the first derivative, if we take this polynomial and calculate its first derivative, we get the following result. Deriving polynomials is straightforward. I hope you don't encounter any issues with it. The exponent of 4 becomes a coefficient, resulting in a 12, and we decrease the exponent by 1. That's why I've written it as 3 here. For the next step, the 3 from the previous derivative goes down, multiplying with the 4, and we subtract 1 from the exponent 3, resulting in 12x squared. Calculating the derivative of 12x squared is straightforward. The 2 comes down, giving us 24. And we decrease the exponent to 1, which is why it's 24x. Now for the derivative of 10x, it's simply 10, because the derivative of x is 1, as you should know. When it comes to a constant term, like the one added or subtracted, its derivative is 0, so we don't need to include it. That's the first derivative. Let's calculate the second derivative and continue finding the next derivatives one step at a time. We apply the same rule. The 3 goes down, resulting in 3 times 12, which is 36. We subtract 1 from the exponent, leaving us with 2. Now how do we derive 12x squared? The 2 goes down, multiplying with 12 to give us 24x, and the exponent decreases from 2 to 1. The derivative of 24x is 24. The derivative of the constant 10, which is just added, is 0. The next step is the third derivative, and it's getting simpler as we go along. The 2 from the exponent goes down, giving us 2 times 36, which is 72, and I subtract 1 from the exponent, going from 2 to 1. So we have 72x. The derivative of 24x is simply 24, because the derivative of x is 1, and the derivative of 24, an additive constant, is 0. We've arrived at the fourth derivative, which is already a simple polynomial of degree 1. What's the derivative of 72x plus 24? It's simply 72, because the derivative of x is equal to 1. I've emphasized this several times, but it's important that you review all these types of derivatives. Starting from the fifth derivative and onward, what happens? The derivative of a constant, in this case an additive or subtractive constant, is equal to 0. So, the sixth derivative would be equal to 0, the seventh derivative would be equal to 0, and so on. All of them would be 0 starting from the fifth derivative. Now let's delve into another example. In this case, I've used a polynomial multiplied by an exponential function. The only tricky part you might encounter here is applying the product rule for differentiation. But don't worry, it's not too complicated. Let's go through it step by step. To start, we need to find the derivative of this function. Where does this derivative come from? As a quick reminder, it arises from the product rule. The product rule tells us that when we're dealing with the derivative of a product of two functions, it's the derivative of the first function, in this case, x squared, which has a derivative of 2x, multiplied by the second function, which is e, raised to the power of x. Additionally, we add the first function without a derivative marked in red here. Next, we multiply this by the derivative of the second function. You might think that we haven't done anything yet, but in reality, we have. The derivative of e to the power of x is one of the simplest derivatives. Please be cautious when dealing with derivatives of e raised to the power of 2x or 3x, those change. Nevertheless, for e to the power of x, the derivative remains the same. I've applied the product rule. Now what can we see? Right here I have 2 times e raised to the power of x. I can extract the common factor and write it like this. See, I factored out the common factor of e to the power of x, and I'm left with 2x plus x squared. You might ask if I can also extract the common factor of x, as I have x here and x squared there. Yes, that's possible, but for clarity, let's keep them separated as a polynomial and an exponential function, okay? The second derivative, we apply the same rule, deriving this, which is a product of 2 functions, using the product rule. How do we do it? Exactly the same as before. The derivative of the first one, now a polynomial, 2x plus x squared. What's the derivative of that? The derivative of 2x is 2, and the derivative of x squared is 2x, which is why I wrote it that way. We multiply by the second one without deriving, plus the first one without deriving, as you can see, times the derivative of the second one. Same reasoning as before. The derivative of e raised to the power of x remains the same. Can I get the common factor again? Yes, of course. I have also simplified a little. I have left e raised to the power of x times 2 plus 4x plus x squared. It's easy to see if you take out the common factor of e raised to x. Here I have 2x, and here I have another 2x. 2x plus 2x is 4x. That's why I put this 4x here. We already have the second derivative calculated. As you can see, it is not excessively complicated to calculate successive derivatives. Now let's delve into the practical applications of these successive derivatives. One of the most important applications is in the context of Taylor polynomials. We're going to explore the usefulness of Taylor polynomials. The idea behind Taylor polynomials is that there are many functions that are not polynomials, and we can express them as a sum of polynomials within a certain range. While we may not be able to approximate a function with a polynomial in all points, except for some special cases, Taylor polynomials allow us to make reasonable approximations in specific situations. For example, if we need to calculate something like e raised to the power of 0.4 and don't have access to a calculator, this can be a problem. Taylor polynomials provide a solution to this problem. How can we calculate e raised to the power of 0.4? To achieve this, we will attempt to approximate the function e raised to the power of x using a linear polynomial centered around the point 0.4, which is our target value. Here's our approach. I'll provide a direct formula for the calculation, but I also want you to understand the concept behind the Taylor polynomial. Our goal is to find a polynomial of the form a plus b x, a linear polynomial where a and b are constants that represent real values. The aim is for this polynomial to closely resemble the behavior of the function e, raised to the power of x in a neighborhood around 0. Now you might be wondering why I chose 0 and not 1. The reason is simple. E raised to the power of 0 is a well-known value, and any number raised to the power of 0 equals 1. But what if we were interested in a different value, say 1.4? I'll address that shortly. We would need to create another polynomial centered at 1, and we'd encounter a numerical challenge because we wouldn't know the exact value of e. Let's proceed further with this process. What am I aiming for? I'm looking for a polynomial that closely approximates the function at the point 0. We have specific requirements. Given that this is a first-degree polynomial, we have 2 unknowns, and to determine them, we need 2 equations. The first requirement is relatively straightforward. I want the function and the polynomial to match at the specific point where I intend them to coincide, which is at point 0. How do I express this requirement? I've designated it with a subscript 1 to indicate its first-degree nature. I stipulate that the first-degree polynomial at point 0 should be equal to the function at point 0. The function evaluated at point 0 is very straightforward. It is simply e raised to the power of 0, resulting in a value of 1. This is why I set it to pass through the point 0, 1. The next condition is what we refer to as a smoothness requirement. We need to ensure that the derivative of the polynomial at point 0 is equivalent to the derivative of the function at point 0. In other words, we are aiming to make sure that the polynomial and the function f have identical tangent line slopes. With these 2 conditions, each providing an equation, and 2 unknowns to consider, we can establish a system of equations that can be solved. Let's try not to get too perplexed at this stage. Naturally, if this is the polynomial represented as a plus bx, you would all be aware of how to calculate its derivative. The derivative of a is 0, and the derivative of bx is simply b. So when I write it down here, I will just use b. Then the condition implies that at 0, I have nothing to substitute. B remains a constant. Now, what is the derivative of the function at 0? Look at the function. The function is raised to x. I told you a little while ago that the derivative of raised to x is one of the simplest. Therefore, it would simply be raised to x, and in 0 it would be raised to 0, which is equal to 1. The important thing is that I obtain this system of equations. The first equation represents the polynomial evaluated at 0, which equals e raised to 0, and the second equation represents the derivative of the polynomial at x equals 0, equal to the derivative of the function at 0, which is again e raised to 0 equal to 1. So, in summary, I have this system of equations, and it's a straightforward one with no complex calculations. I find that b equals 1, and since there is no b in the first equation, I can directly conclude that a equals 1 as well. This results in the polynomial y equal to x plus 1, which is a simple straight line. Is this useful for approximating the value of the exponential function? The answer is yes. If we evaluate the polynomial at the point 0.4, it equals 1.4, which is straightforward. 0.4 plus 1 is 1.4. On the other hand, the actual value of the function at 0.4, calculated using a math program, is approximately 1.4988, etc. As you can see, the values of the polynomial and the function are quite close. You might think this approximation is not precise enough, and you'd like more decimal places. We will explore how to achieve that shortly. However, with the simple work we've done, you already have an approximation for a number you might not know the value of, like e raised to 0.4, which we know is roughly 1.4. The absolute error in this case is 0.09918, which is remarkably good for the minimal effort we've put into this calculation. Here's a graph illustrating the comparison. The exponential function is shown in blue, and the polynomial I just calculated is in red. The key point to observe is that they match perfectly at 0. If we look at 0.4, there is a slight displacement, and this results in an error between the line and the exponential function. However, these errors remain quite small, within a certain range around 0, approximately from here to here. On the other hand, if I were to approximate the value at 1, you can see a considerable gap between the polynomial and the exponential function. In such cases, it wouldn't be appropriate to calculate e raised to 1.2 or 1.4 using this polynomial. Yet, for estimating e raised to 0.4, the polynomial provides a very good approximation. Let's repeat the process using a polynomial of degree 2. The procedure is the same, and this time we consider a function of the form a plus b x plus c x squared. What do I need to do? Since I have three unknowns, a, b, and c, I require three equations to solve the system. The equations are straightforward. The values at 0 match, the first derivatives coincide, and now I'll also demand that the second derivatives are equal, ensuring a smooth transition. Thus, I obtain this system. It involves taking the polynomial, substituting x with 0, then differentiating it. We will do that 3 times. In this part, you just take the function provided at the beginning, e raised to the power of x, and substitute all instants of x with 0, which all give you e raised to 0, which equals 1, 1, 1. If I were to solve the system, I won't do it right now as it's a bit more complicated. I would arrive at the next polynomial, which is 1 plus x plus 1/2 of x squared. Notice that all we've done is added one more term when considering this problem. This part here was exactly the same as before. With this polynomial, I achieve a slightly better approximation than the previous one, that of a polynomial of degree 1, because it's a bit more accurate. If I replace the x in this polynomial with 0.4, I get 1.48. A little better, because the value we had before was 1.49. What is the error now? It's 0.011. We've reduced it somewhat, which is quite a considerable improvement. Can we continue this process? Well, yes. Instead of taking a polynomial of degree 2, we can take a polynomial of degree 3. But of course, solving these systems that we are proposing is not easy. We would have to work a bit to obtain the coefficients of the polynomials consistently. Is there a different way to do it? Yes, of course. Excuse me. I wanted you to see this graphically. The blue curve represents e raised to the power of x. Now, as you can see, the polynomial of degree 2 is a better approximation than the straight line. It approximates a bit more accurately, and the interval where it matches the function has expanded. To compare them, take a look. The new degree 2 polynomial is in pink, and the blue curve is the exponential function. As you can see, the degree 2 polynomial's graph is much closer to the exponential function than the straight line. There is a way to directly calculate these approximations, and it is called Taylor polynomial of degree n. It's defined with a formula that's not very complicated to learn. I've denoted it with n here, because you can calculate this polynomial for any degree. The formula is the following: f of a plus f prime of a times x minus a plus the second derivative of a divided by 2 factorial. 2 factorial is 2 times 1. Times x minus a squared plus the nth derivative of x divided by n factorial. To clarify, n factorial would be n times n minus 1 times n minus 2, and so on, all the way down to 3 times 2 times 1. And multiplied by x minus a raised to the power of n. It's a formula that you can apply at any time. If you know it, it's really very easy to use. The only thing you need to keep in mind is that you require the derivatives of the function at all points. And that's just differentiation. It's not too complicated. One more thing to note. When you take the point a as 0, this polynomial, instead of being called Taylor's polynomial, is usually referred to as Maclaurin's polynomial. Just a side note. Let's calculate the Taylor polynomial of the natural logarithm of x centered at x equal to 1. We'll use it to approximate the value of the logarithm of 1.2. For this, we need the function, as well as its first, second, and third derivatives. The derivative of the natural logarithm of x is known to be 1 divided by x, which can be expressed as x raised to the power of minus 1 for convenience in differentiation. The second derivative is derived by applying the same rule, with the minus 1 coming down, and after subtracting 1 from the exponent, we have minus x raised to the power of minus 2, equivalent to minus 1 divided by x squared. For the third derivative, we apply a similar process. The minus 2 comes down, giving us minus 2 times minus 1, which is 2. And after subtracting 1 from the exponent, we get 2 over x cubed. What's the next step? We'll substitute each of these x with 1, the value at which we're centering our polynomial. So here's what we get. The function evaluated at 1 equals the natural logarithm of 1, which equals 0. The first derivative, upon substitution, is 1. For the second derivative, when we plug in c equals 1, we end up with minus 1. And lastly, for the third derivative, substituting 1 gives us 2. Now, what's the resulting polynomial? If I go back to the formula I mentioned earlier and substitute f of a with f of 1, here's what we get. We've reached order 3, which is our maximum order. So, let's do the substitution. For f of 1, we put 0. For f prime of 1, it's 1. F prime prime of 1 becomes minus 1, and f prime 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 of 1 is simply 2. This leads to the following expression. Let's simplify it a bit, and we end up with a degree 3 polynomial. Does it provide a good approximation? Indeed it does. The blue curve represents the natural logarithm function, while the slightly reddish-pink one is the Taylor polynomial approximation. As you can see, it fits quite nicely, offering a pretty accurate approximation. If you'd like to explore this further, take a look at this graph. On the same graph, I've displayed the degree 1 polynomial that approximates the logarithm at x equal to 1, as well as various polynomials of different degrees up to 10. Observe how these polynomials gradually converge and adapt to the function. Clearly, there's a point where the two functions become nearly indistinguishable in this region. The closer the degree of the polynomial is to the function, the more similar they become. However, outside of this region, they diverge significantly. The error is quite negligible, given that the result for the logarithm is 0.1823, while the polynomial yields 0.1826. As a final note before I conclude, I'd like to emphasize that if the nth derivative exists, this limit tends to 0. In other words, the polynomials progressively approach the function, resulting in smaller and smaller errors. Today, we've covered successive derivatives and the Taylor polynomial. I hope this proves useful in the future. Thank you for your attention.